So this chapter is called Radiation and Spectra. Some words we're going to learn about are the atomic spectrum, or also called the emission spectrum, the absorption spectrum, a black body or thermal radiator, the continuous spectrum, the Doppler effect, the electromagnetic spectrum. That's all types of all types of radiation, from radio waves through gamma rays. Energy levels, excitation, frequency, ground state, isotope, nucleus, photon, radio velocity, spectrometer, Stefan-Boltzmann law, wavelength, and Wien's law. So this is really about light and atoms, and how they interact, kind of. And so we'll start by just talking about light. Light is a wave, and so if I go to if I just draw a picture, there are two basic types of waves. So if a wave is traveling this way, this is a transverse wave. Because the oscillation up and down is perpendicular to the direction of motion. Oops. So light is a transverse wave. There's another type of wave that we won't really talk about too much, but it's called a longitudinal wave. Sound is an example of a longitudinal wave, but you can also have a longitudinal wave on a slinky, right? And so if I take a slinky and I create a pulse on it like this, you can see that the pulse is, so this would be a transverse wave, and this would be a longitudinal wave. The compression is along the direction of motion for a longitudinal wave and perpendicular for a transverse wave. And so that's the difference between those two. Light is a transverse wave, and so light is perpendicular oscillating electric and magnetic fields, and so you can kind of draw the electric field this way. Just draw a wave. That wasn't very good, but you get the idea, and so on. Right? And so this is the electric field oscillating up and down as the wave is traveling this way. That's the velocity of the wave, right? And then if I could draw it, I'll try to draw it, but I won't be very good at the magnetic field. So if the electric field is oscillating this way, the magnetic field will be oscillating into and out of the board. And so I don't know how you draw that, like this maybe. And so it's oscillating like this. Does that make sense? So the magnetic field is oscillating this way, while the electric field is oscillating up and down. And so we usually use B for the magnetic field. Don't ask me why. Okay, so we can look at this and we can say, let me just, this is a little bit of truth about waves in general. If I have an ocean wave or any kind of wave that's just an oscillatory, that's just a transverse wave of some kind, man, I'm not getting very good ones. All right. So the distance between successive peaks is a wavelength. Right, that's what we call the wavelength of the wave. By the way, it's also the distance between successive troughs, or the distance between halfway up the hill to halfway up the hill, and so on. Just pick two like points, and that's a wavelength. And we use the Greek letter lambda for that. This is the velocity v, right? And then the frequency is the number of waves per second. And so if you know, let's pick something in the ocean, say, just for, because all waves kind of act the same. So if I say my wavelength is, I don't know, 2 meters, which is about 2 yards. And then if my frequency is like, I don't know, let's say 3 waves per second. All right, the frequency is the number of waves per second, so it's 3 waves per second. Well, if they're 2 meters apart and they're 3 waves per second, that means my velocity is 2 meters times 3 waves, so it's 6 meters per second. That's my velocity. The velocity of a wave is equal to the wavelength times the frequency for any wave. And so it's easy to remember, hopefully. I'm not going to ask you to do too much with these. I won't ask you to do any too serious calculations, but you ought to at least sort of understand how that works. Wavelength times frequency is velocity. So here's a picture of the sun in ultraviolet light. It's false color. Human eyes can't see ultraviolet light, but you can see that this doesn't look like a normal picture of the sun. So it's important for us to understand other ranges of wavelengths besides visible light. Things look different in different wavelengths, and we get new information by looking at things in the X-rays or in ultraviolet or infrared and so on. There's a picture of James Clerk Maxwell, whose name comes up from time to time. You might have heard of him. He was sort of the father of our understanding of light. So these are some, if you look at these guys, these are some surface waves on water, which you're familiar with, right? And you can kind of see they've got a small wavelength there, and if you were standing there, you would watch them go by with some velocity. You can calculate the frequency. Here's a nice picture of a wave with a crest and a trough and a wavelength and so on. Okay, so let's talk a little bit about intensity. So you can kind of see here that the closer you are to the light source, the more intense the light is. So if you just look at the light that's coming into this square, right, as it gets farther and farther away from the light source, this could be a star or a light bulb or something like that. The same light that was all packed into this one little square, if you're twice as far away, is now packed into 4 little squares, right? If you're 3 times as far away, it's packed in into 9 squares. And so we say light obeys an inverse square law. That is, the intensity, how bright the light appears, is goes inversely as the square of the distance you are. It's 9 times dimmer. When this light is spread out over 9 times the area, then it's 9 times dimmer when it's 3 times as far away. Let's see if I can pull that other one up for a second. So we talked a little bit about these guys. So here's the inverse square law of light. I didn't say the speed of light is about 3 times 10 to the 8th meters per second. That's equal to 186,000 miles per second, and so that's we talked about this before. That's about the distance to the moon. The moon's about 240,000 miles, so it takes a little more than a second for light to get from the Earth to the moon, and obviously a lot longer for objects that are much farther away. So what we're talking about now is the inverse square law, which means the intensity of light varies as 1 over the square of the distance you are from it. Here is what we call the brightness luminosity relationship. It's the brightness is equal to the luminosity over 4 pi times the distance squared. And I'll talk about these through the semester, this particular equation. Brightness is how something appears to you. I'm on the wrong sheet here, so just let me switch back. There we go. Sorry, I'm talking about this relationship. The 1 over r squared variation of light intensity with distance. So this equation here, it's the relationship between brightness, which is the B, and the luminosity, which is L. And I think you'll have a sense for all of these. So brightness is how bright something appears when you look at it. If you're really near a bright light bulb, it appears really bright. As it gets farther and farther away from you, it gets dimmer and dimmer. The brightness decreases with the square of the distance. So if you're twice as far away, it's 4 times dimmer. If you're 3 times as far away, it's 9 times dimmer. Because that light is spread out over a bigger and bigger area, just like we saw in the picture a second ago. Well, what is this luminosity? This luminosity is sort of the absolute wattage. So if it was a 100-watt light bulb, the luminosity would be 100 watts. That's what the luminosity is. The luminosity just tells you what the original light source, what its power rating is. The brightness depends on how far away you are. And so there are 3 unknowns in this problem: brightness, luminosity, and distance. As you know from your algebra class, I'm not going to make you do any real algebra in here, that if you know any 2 of these, you can determine the 3rd one. And so if we know the distance and the luminosity, we can calculate the brightness. If we know the brightness and the luminosity, we can calculate the distance. If we know the brightness and the distance, we can calculate the luminosity. This is very useful for people who study stars and things like that, because generally with a star, you can know the brightness because that's just how bright it appears. You can just measure that when you look at a star with a little instrument or something. And by the type of star it is, by the kind of light it gives off, we can tell what its wattage is, what its luminosity, what kind of light bulb it is. And that allows us to tell how far away it is, knowing those 2. And so this is a really important relationship, the brightness-luminosity relationship. As you get farther from a light source, it gets spread out over a larger and larger area that increases with the square of the distance, so the intensity decreases at that rate. So let me go back to here. Okay. So light varies in intensity with the square of the distance inversely. And so if it's twice as far away, the light gets 4 times dimmer. If it's 3 times as far away, the light gets 9 times dimmer. This is called really the brightness-luminosity relationship. In this equation here, B is the brightness, L is the luminosity, and D is the distance. You know what 4 and pi are, right? Brightness is just how bright something appears to you. A light that's near your face will appear really bright. If it's really far away, it'll appear dimmer. And that the value of that is called the brightness. D is how far away the light source is. This L is called the luminosity, and it's kind of like an objective brightness rating of the light source. So, for example, a 100-watt light bulb would have a luminosity of 100 watts, and so on. So the L is just kind of a property of the star or whatever the object is you're looking at. B is what you see, and D is the distance. Well, if you know from algebra that if you have you have 3 unknowns in this equation. If you know any 2 of them, you can calculate the 3rd one. I won't ask you to do that, but we'll be talking about it a little bit. And so if I know the luminosity and the distance, I can calculate the brightness. If I know the brightness and the luminosity of a star, I can calculate how far away it is. And this is the way this equation is most often used. We measure the brightness because that's what we see. We can just aim an instrument in it and it'll tell us how bright it is. And then we know what kind of star it is by the kind of light it gives off, and that tells us the luminosity. And then we can use this equation to calculate how far away it is. And this gives us distances to things in the universe, and so it's very important for that equation is, at least for fairly nearby stuff. We talked about the wave model of light. There's also a particle model of light, which we'll get to. Light was originally thought to be a wave, and Newton taught it that way, or thought of it that way. But later on, we began to see light acted much more like the way water waves or sound waves do, and so we started treating light as a wave, and then Einstein found ways that it was a particle, and now we kind of treat it as both. All right, so let's talk about the electromagnetic spectrum for a minute. I'm just going to talk these through, and I'll tell you what I want you to know about these. The electromagnetic spectrum is just all the wavelengths of all light of all different types, from radio waves to what we call gamma rays. And we give these guys names for regions of wavelengths. I'm not going to spend any real time on that. I'm just going to I'm going to tell you what the longest wavelengths are and how they're used. And you'll have heard of most of these, right? The typical bands that we talk about. There's no well-defined separation between these guys, by the way. But we name them according to kind of historically how they've been used. So the longest wavelengths of light are called radio waves, and then the next longest is microwaves. Slightly shorter than that. Yeah, next longest is microwaves, and then slightly shorter than that is infrared light, and then after that becomes visible, and then after that comes ultraviolet, and then X-rays, and then gamma rays. And those are in order from longest to shortest wavelength. They're also in order from smallest to largest frequency. If you remember, we said, I'll just write this over here since it's in the corner of the screen. We said the speed is equal to the wavelength times the frequency. Well, they all have the same speed, right? All light travels at the same speed, at least in a vacuum. And that means if your wavelength is longer, your frequency has to be smaller so that you get the same velocity. And so light with long wavelengths have small frequencies. Light with small wavelengths has large frequencies. So the product doesn't change, right? And so I'll just go through this list, and I kind of want you to know, the order of these guys in terms of longest wavelength to shortest wavelength, or smallest frequency to largest frequency. Either one of those you should be able to do. Radio waves are primarily used for communication. Microwaves are used for cooking and increasingly communication. Infrared light is used for heating and communication. So infrared is your TV remote control, for example. Microwaves and radio waves are all sorts of cell phones and television and radio and all this stuff. So visible light is used for seeing. Hopefully you're aware of that. Right? These are all bands, by the way, that are important in astronomy. We look at things in all of these different wavelengths because information comes out in all different wavelengths, different information. Ultraviolet light is used for sterilization, also for cancer. I'm really just joking about that, but ultraviolet light is dangerous to humans. All of these high frequency wavelengths, short wavelengths, all these high frequency radiation is dangerous, because they carry much more energy. And so ultraviolet light is often used in tanning beds, for example, which you shouldn't use. It's just dangerous to your skin, regardless of what your skin pigment is. Ultraviolet light is dangerous. Same thing with X-rays and gamma rays. These you're not as exposed to, but you can be. People who are flight attendants and things like that have their airtime is limited because they're exposed to higher amounts of radiation higher up in the atmosphere. The atmosphere filters that stuff out. So ultraviolet light is often used for sterilization. You can kill bacteria, and so there's some water filtration systems that use ultraviolet light. Sometimes those are used to kill microbes. The same thing with radioactive materials. They can be used to kill microbes. They're not dangerous if they're not shining on you. You don't want to consume radiation, X-rays or gamma rays. That is to say, you don't want to consume objects that emit X-rays or gamma rays. It is perfectly safe to consume strawberries that have been irradiated by gamma rays, because once they're light rays and they've been absorbed by the strawberry or whatever it is, and the bacteria have been killed, that light is no longer there, and you're not in any danger at all. Another little tidbit is people are always worried about their cell phones causing cancer of some kind. Cell phones emit radiation down here. This stuff is not dangerous, and so it's very unlikely you'll have any real problems with radiation from cell phones. It's only the higher energy stuff, and this is really regulated by the government. You're not easily exposed to this stuff unless you're working in a medical place or some kind of a science lab or something like that, military. Astronomers want to know how these different bands pass through the atmosphere. Most radio waves can pass through, microwaves can pass through. The atmosphere is mostly opaque, that is, it doesn't allow infrared to come through, but it allows visible. And then it's opaque to ultraviolet, X-rays, and gamma rays. This is really good because the atmosphere stops all this dangerous radiation from getting to us. And so I think there's a picture of that on the slide, if I can find it. Yeah, there we go. So let me just see if I... so this kind of shows you, so over here on the right, the longer wavelength radio waves don't get in, but there's a wide band of radio and microwaves that get through easily, and that's why we can have radio telescopes on Earth. And then there's a region in the infrared where it's opaque, and this is part of the global warming issue because the Earth heats up, it emits infrared, and it can't get out because the atmosphere just absorbs it, it gets warmer. And so here's the visible spectrum, and the visible spectrum is a teeny tiny fraction of all the light that comes in. And then if you notice, a little bit of the ultraviolet gets through the atmosphere, and not really relevant to astronomy very much, but it hurts our skin. I mean, it is used by astronomy, and so if you want to look at if you want to do astronomy up in this wavelength range, up here in X-rays or gamma rays or ultraviolet, you really need to have spaceships above the atmosphere, because that stuff doesn't penetrate the atmosphere. Same thing with infrared, and same thing with long wave radio waves. Okay. Here's a picture of just the sort of a fisheye picture of the universe in the X-ray spectrum. It's very different from what you see in the visible spectrum. So we're going to talk about how light is radiated by objects. Normally when we look at things like a shirt or a book, you're looking at reflected light. But objects also radiate their own light. They create and emit their own light. And that's really what we're looking at in astronomy often, like when we're looking at stars or galaxies or something. When you're looking at the moon, you're looking at reflected light. But when you're looking at a star, you're looking at emitted light. And that's what we're looking at with this graph. And so what I want you to do with this graph is just think about it in terms of a single object, like a log on the fire, or an iron poker or something like that. When it's at about 3,000 degrees Kelvin, or 3,000 Kelvin, you can kind of double that to get Fahrenheit, so 3,000 Fahrenheit. These curves on here, this is a graph of intensity versus wavelength. And so if you'll notice, all of these curves cover the whole graph, or at least to where you can kind of see it. And what that means is that this object that's at 3,000 Kelvin is emitting light at all wavelengths across the bottom. Curve goes all the way across. When it gets down to zero, it keeps going. It's just like it's right along the axis. And so what you can see is this same object now heated up to 4,000 Kelvin, or then heated up to 5,000 Kelvin, or to 6,000 Kelvin, and so on. The intensity of light it emits at every wavelength increases. That is to say, the yellow curve is everywhere above the orange curve, the green curve is everywhere above the yellow curve, the blue curve is everywhere above the green curve, and so on. And so
let's start with the 3000 Kelvin curve here at the bottom. It's emitting the most light in this wavelength over here. Notice the visible spectrum is over here, and I'm at a longer wavelength now than the visible spectrum, than the red end of the visible spectrum. So this is probably in the infrared or something like that. And so this one is emitting most of its light in the infrared, as is this one. But now the green curve is now emitting most of its light in the red, and then the blue curve is emitting most of its light in the yellow, right? And so that is to say, maybe not most of its light, but the yellow light is the most common light in its that's being emitted by it. That's this is the intensity versus wavelength. So the highest intensity for any wavelength is the yellow here, the red here, the infrared here, and the infrared or microwaves here. And so you can see as this object gets heated up, the peak wavelength moves to shorter and shorter wavelengths, right? And so if we were to keep going, eventually the peak would be over in the ultraviolet, and the curve would just drop way down on this side all the way through the visible spectrum. Well, what do these objects look like? This 3000 Kelvin object, if you were to just look at it, well, you only see visible light with your eye. And so this orange curve here at the bottom emits more red light than any other color, and so it'll appear mostly red. And this is consistent with what happens when we get things hot. Things tend to glow red when we heat them up. By the way, the same thing with the next two, right? The yellow curve is also emitting more red light than any other color. Same thing with the green one, more red light than any other color. And so these will appear red or reddish as you heat them up. This is the same object, again, same log, it's getting hotter and hotter, or same piece of metal. Now all of a sudden the peak is in the middle. This object will start to appear white, because now it's got kind of an equal mix of all colors, you might say, or at least as much red as purple, or close to that. And so this is kind of how the sun looks. It emits kind of a peak somewhere in the yellow, and then the rest of them kind of balance out and looks mostly yellow or white. If stars that are hotter than that, well, their peak will be in the ultraviolet, and so all the way across the visible, the highest frequency, the wavelength that emits the most light is the blue. And so those stars will appear blue. And so cool stars in the 3000 Kelvin range appear red. Middle stars, like the sun, appear white or yellow. And really hot stars appear blue. So, as the temperature increases, the total amount of light increases dramatically. Let me just get up to that for a second. The peak of the radiation curve, the most emitted wavelength, moves towards shorter wavelengths as the object gets hotter. The total amount of light, if you notice, if I go back to that previous curve, you can see that the total amount of light is like the area under these curves. And so you can see that as the thing gets hotter, it emits way more light as it heats up. It emits more light at every frequency or every wavelength. And so the total amount of light is much higher as the object heats up. And so there are mathematical formulas for this, which we'll just talk about. And so, for example, there's something called Wien's law. Wien's law says that the maximum wavelength, in other words, the peak wavelength in those curves we were just looking at, is 3 times 10 to the 6 divided by the temperature in Kelvin. And so as the temperature gets larger, right, we all know how fractions work. As the denominator gets bigger, the numerator doesn't change. So as the denominator gets bigger, the fraction gets smaller. And so the maximum wavelength, the peak of that curve, the wavelength for the peak of that curve, gets smaller as the temperature rises. So now we're going to talk about the energy flow. And this is the Stefan-Boltzmann law. And we call this the energy flux, but flux just means flow. It's the outflow of energy from any hot object. And it turns out that the rate of flux is the power divided by the area. It's and that's equal to this quantity sigma, which is a constant, times the temperature to the fourth power. And that's really all I want you to know about this. There's some constant here. It doesn't matter really what its value is, but how the rate at which something radiates power goes as the fourth power of its temperature. And so something that's a little hotter produces a whole lot more power. And so I'm just going to give you a little example down here. I think somewhere down here. Well, I do two things down here. I calculate the power emitted by the sun, and I rearrange this formula a little bit from the one we just had. So let me just scroll back up there just for a second. So if you look right at the top here, I guess I should get that off the screen for a second. The flux is the power over the area, and that's equal to this thing sigma times temperature to the fourth, and so that means the power is equal to the area times this Greek letter sigma times the temperature to the fourth. Turns out we can evaluate this for the sun. The power emitted by the sun is the area of the sun times this constant, which we showed you, it doesn't matter what it is, times the temperature of the sun to the fourth power. And so the area of the sun, it turns out, is the area of a sphere. You don't need to know this. Is 4 pi r squared. And we can evaluate this. R is the radius of the sun, and we can plug all these numbers in, and it turns out that comes out to 4 times 10 to the 26th watts. So this is the kind of light bulb you would need if you wanted to replace the sun, right? That temperature to the fourth power, that's 5800 times 5800 times 5800 times 5800. That's a really big number. And when you're really hot, that number gets really big really fast because you're multiplying it by itself 4 times. And so we can do a quick example down here in part D, and I'll stop for a minute. Consider two stars A and B, which are the same size. Suppose the temperature of A is 10 times larger than the temperature of star B, right? So temperature A is equal to 10 times temperature B. What does that say about their relative power outputs? Well, we just said the power is equal to the area times sigma times the temperature to the fourth power. I have these little subscript A's to let you know that here I'm just talking about star A, right? Remember, they're the same size, so the area of A and the area of B are the same, but the temperature of A is 10 times the temperature of B. And so temperature to the fourth is just temperature to A times temperature A times temperature to A times temperature A, right? But that's just 10 times temperature of B, and so I can replace all those temperature A's with 10 times temperature B's, and continue this equation. It gets really long here, but then we're free to multiply numbers in any order, and so we can take the 10 times 10 times 10 times 10 and make it 10,000. And so that's the area of A times 10,000 times sigma times temperature of B to the fourth power, because we had TB times TB times TB times TB. But that's just, I can rearrange the order, that's just 10,000 times the area of B times sigma times temperature of B to the fourth power, which is 10,000 times the power emitted by B, because the power emitted by B is just area B times sigma times temperature of B to the fourth power. And so what this says is the power emitted by star A that's 10 times hotter is 10,000 times the rate of the power of B. And that's really important because stars only have a certain amount of fuel, and if I'm burning up my fuel 10,000 times faster than you are, then I last 10,000 times shorter. And so if you live 10 billion years, like the sun, a star that's the same size and 10 times hotter will only live 1 million years. And those numbers are very different, 10 billion versus 1 million. That's a millionaire versus Bill Gates or something like that. And so the temperature of stars play a big role in how long the star lasts before it runs out of fuel. So one last thing about the power output. Notice that in this example where the temperature of star A is 10 times the temperature of star B, then the power output of A is 10 times 10 times 10 times 10, or 10,000 times the power output of star B, right? So if temperature of star A was twice as big as the temperature of star B, it'd be 2 times 2 times 2 times 2, or 16 times more power. It's whatever that factor is to the fourth power. And so that's why a small increase in temperature produces a big difference in power output. Hot stars don't live nearly as long as cooler stars. The coolest stars live the longest time. The sun will live about 10 or 12 billion years. Smaller stars like red dwarfs can live 1 trillion years, longer than the age of the universe. They've got extremely long lifetimes. So we're going to talk about spectroscopy, which is kind of like breaking down light into its component wavelengths. For example, we've all seen the experiment where you take sunlight and run it through a prism and get a rainbow of colors, right? You can even see that in a rainbow. The white light from the sun is broken down. We're seeing the spectrum. There's several different types of spectrum. I'm going to show you a video in just a minute of a couple of these. But there's the emission or atomic spectrum. So let me just pull the text up here. So there's an example of a continuous spectrum, right? This is what you would get from the light bulb or something like this. This is sort of the range of wavelengths that the human eye can see in the visible light. So from somewhere around 750 nanometers to 380 nanometers, or somewhere in there. Usually we say 400 to 750, but eyes can vary. And so these would be all the colors you see in a continuous spectrum.
So this is a sort of a standard filament type light bulb. It's got a metal filament inside, and you can kind of see it in there, maybe. Just a metal filament running up the side there. When I turn the light bulb on, the way old style light bulbs like this one work is current runs through that filament, and it gets really hot, and the heat causes the light bulb to radiate. And then so I can learn something about the kind of light that's coming off it by taking this prism and holding it in front of my camera. And then when I look at the light bulb there, if I go off to the side a little bit, I'll see a rainbow of colors. The prism bends the light coming from the light bulb. There's the light bulb, right? I can go to either side, and I'll see a full spectrum of colors. A hot, dense object like a metal filament radiates all frequencies of light. You're seeing all the colors of the rainbow right there across the middle of your screen. And that's because every color of wavelength, every wavelength of light is being emitted by that hot, dense object. So now I've got something a little different. These are called gas discharge tubes. There are 3 of them here. This one's helium, and the middle one's hydrogen, and the one on the right is, I think, mercury. So helium, hydrogen, and mercury in separate glass bulbs, and I can alternately turn one or another of them on. And so right now the helium is hooked up, and so if I turn that light bulb on, you'll see that it glows. The helium one glows. And what's interesting about it is it glows sort of like the filament light bulb we saw does, except it's a different process. A huge voltage, notice that says danger 5,000 volts, right? Whereas our light bulb ran off 110 volts, here you put 5,000 volts across this gas discharge tube, and then the gas glows. And it's a different process. It's kind of like what's used in fluorescent lights. And what's interesting about it is a glowing gas does not give off all frequencies. You won't see a full rainbow here. When I take this grating and put it in front, you'll see just a couple of lines. Do you see those colored lines there? Those correspond to very specific frequencies of light that are being emitted by this helium gas. You can see it kind of, I think it's repeated there a couple of times, but it's just very selected wavelengths are emitted
by heated gas as opposed to a solid dense object like a filament, like a light bulb filament that's really hot. And so these are different processes, and we're going to be talking about this. I'm going to give you another demo here. So this is what helium looks like, and kind of keep that in your mind, or scroll back to it, and I'll do hydrogen next. So here it is again. You see a continuous spectrum here across the top, and then below that you see several discrete spectra like you saw for helium in the video just a minute ago. So here's what sodium looks like if you have a gas discharge tube that's run through a diffraction grating or a prism. Here's what hydrogen looks like. Here's what calcium looks like. Here's what mercury looks like. So if there's hot mercury gas somewhere 1 billion light years away, all we have to do is aim our telescope at that object and then break the light down this way, and we can say, oh, that's mercury way off there somewhere, right? This is how we sort of learn the composition of the universe. We know that it's 90% hydrogen because 90% of the stuff we look at gives this hydrogen spectrum. Here are the 3 basic types of spectrums that you can see. The first one is just a hot filament, so you get a continuous spectrum. The second one is a hot gas, right? So a filament is very densely packed atoms that are stuck together really close, and they vibrate in such a way to produce a continuous spectrum. In a hot gas, you see something different. You see these discrete lines spaced out according to what their colors are. And then the combination of these two produces what we call an absorption spectrum. And so in an absorption spectrum, you have a continuous spectrum produced by a hot solid object. These are usually stars if you're out in space. And then you have a gas somewhere between your diffraction grating, which is at the end of your telescope, and the star. Usually that's just the gas around the star, so it's usually just attached to the star somehow, but it doesn't have to be. You can be looking through a cloud of gas that's between you and the star. What happens then is instead of the gas emitting these bright lines of light like we saw for the emission spectrum, they actually absorb the light. And so a cool gas will absorb the light. It actually retransmits it, but since the light was going this way, the cold gas will retransmit it in any direction. And so only a small fraction of it ends up going in the forward direction the way it was going when it started. And so you end up seeing dark lines where the bright lines from the continuous spectrum would have been. And so this is an absorption spectrum. Notice in either an absorption spectrum or an emission spectrum, you can tell what flavor of atom, what element is doing the absorbing or the emitting, because the spectrum, the lines that are the fingerprint of that atom are right there in either against the dark background for an emission spectrum or against the continuous spectrum for an absorption spectrum. So here, let me just pull another slide down. Here is the spectrum of the sun, and so it's a continuous spectrum. It's an absorption spectrum. It's a continuous spectrum with an absorption spectrum on top of it, right? And so all these dark lines, all these zillions of dark lines you see here, notice that this has been folded over a whole bunch of times. The lines go horizontally. They're very thin and go horizontally, and we should string all these colors into one continuous strip that's 3 millimeters wide and would be a mile long, not a mile long, but really long, right? And all those dark lines can then be broken down into the specific elements they represent. And so we can tell all of the elements that are in the gas that's surrounding the sun and any gas that's between us and the sun. So this would include gas that's in our atmosphere or gas that's in space between us and the sun. And so you can get really detailed information by aiming your telescope at a star and then getting an absorption spectrum from that star.